Okay, please begin now. Hello, Unnati madam, please begin.
Yes, sir. Yes, sir. Shall we begin, sir, now?
Yes, madam.
Okay, fine. So, all the respected faculty members, researchers, and your student, I, Dr. Unnati Joshi, Dean, Faculty of Engineering and Technology, Waterloo University, along with my colleague, Professor Manish Pandya, who is associated with the Electrical Engineering Department, welcome you all for today's webinar. This webinar is entitled as Introduction to Advanced Automotive Battery and Electric Vehicle Model. As we all know that electric vehicles are either partially or fully powered by electric power. They basically use the electricity as a power source instead of an internal combustion engine, which generates power by burning a mix of fuel and gases in conventional vehicles. So these electric vehicle is seen as a very promising replacement for current generation automobile, and these vehicles are very effectively addressing some of the burning issues like rising pollution, global warming, depleting natural resources, and so many. Also, electric motors, they react very quickly. So electric vehicles are very responsive and they give very good amount of the torque also. Also, the advantage as far as electric vehicles are concerned, they digitally get connected than conventional vehicles, providing the option to control the charging using a smartphone app. But it is not so that all the advantages are there. A couple of limitations and challenges are also there. So to provide a thorough exposure for the advanced automotive battery as well as electric vehicle model, I take this opportunity to invite Dr. Satyam Panchal. Dr. Satyam currently works as adjunct professor in the Department of Mechanical and Mechatronics Engineering at University of Waterloo, Canada. His research area is thermal management of lithium-ion batteries for electric vehicles and hybrid electric vehicles. He is currently working on a project called Battery Life Cycle Management for Ford Escape, PHEV and EV. And the project is supported by Transport Canada. He is also actively working on the research area of lithium-ion battery, thermal degradation, electrochemical, and CFD modeling. For battery pack testing and modeling, he worked at Green and Intelligent Automotive Lab at University of Waterloo. He has to his credit more than 25 referred articles in highly reputed international journals. He is also a member of Professional Engineers Ontario in Canada since 2016. Additionally, Dr. Panchal is also an excellent teacher and won 5 awards in consecutive years for teaching excellence at University of Waterloo. So with a great privilege, I welcome you, sir, and the digital stage is all yours. Over to you, sir.
Thank you. Thank you so much, Dr. Unnati, for my introduction. Before I start my presentation, is my audio clear to everyone?
Yes, sir.
Good.
You are very well audible.
Sure. Thank you. So since Dr. Unnati has already introduced me, I would like to skip a couple of slides for my personal introduction. But good afternoon to everyone. And my name is Dr. Satyam, and I'm from University of Waterloo from Canada. And my today's presentation topic is Introduction to Advanced Automotive Battery and Electric Vehicle. Now, I would like to skip this slide because it is already introduced by Dr. Unnati. And about my educational information, I did my bachelor and master's from India. Then I left India in 2004, so almost 16 years. And then I did my MS from University of Waterloo, then PhD and postdoc. So during my master's, I worked on impact of vehicle charge and discharge cycles on thermal characteristics of lithium-ion battery. And for my PhD, I worked on cell level testing and modeling. And for my postdoc, I worked on pack level thermal testing and modeling. About Google Scholar, you can see, or you can type my name and you will find my citations and like a couple of papers recently published in 2020 and with the hysteresis. So this is another new area which I will explain later on about the hysteresis and open circuit voltage modeling. About awards and membership. So during my study, I was very hardworking student, and I don't want to go through all these awards, but I won like OGS called Ontario Graduate Scholarship and David Johnson Governor General Award from Government of Canada, and I am a member of Professional Engineers Ontario, which you can see over here on the right hand side. So I purposefully pasted this picture because like this Ph.D. license is very important in Canada. So if you want to work in a design department or in a the government sector where you can sign and seal the document or sign and seal the design, then you have to have this license. And based on like 5 years experience under any Ph.D. in Canada, you can get this license. So this is the valuable license which I got before 2 years after getting 6 years experience under my 2 professors. And even like University of Waterloo also selected my name for CEAB called Canadian Engineering Accreditation Board during 2013 and 14. In continuation of that, as Dr. Unnati said, that I won like 6 times Outstanding Teacher Award based on students' recommendation from University of Waterloo, especially for Engineering Thermodynamics 1 and Thermodynamics 2 and Heat Transfer 1 and 2. So I was teaching undergrad student like 3rd year and 4th year for heat transfer and 2nd and 3rd year for thermodynamics. You can see here the Gaia lab. So Gaia is called the Green and Intelligent Automotive Lab, and it is recently opened. We received almost $10 million equipments from Michigan State, from United States of America, where you can see over here. So this is my pack level battery testing and battery cell and pack testing, where in this laboratory we can do any kind of testing, including the cell level, module level, and the pack level. Then we can do CIL called component in loop validation. Then we have a facility for engine dynamometer testing also. Here you can see a vehicle called the autonomous vehicle, means the driverless car, and that is the new research area right now. People are working at the Gaia laboratory. You can see here the VICE is called the Waterloo Institute of Sustainable Energy, and they publish a magazine every year, and they selected my paper like the VICE for the Waterloo magazine, and my paper was highlighted in their magazine. On the right hand side, you can see 2 professors. One on the left hand side with the red puppy on his shoulder is known as Professor Roydon Fraser, and he's a chair in mechanical and mechatronics engineering department, and he is my main professor, and he is a principal investigator for Green and Intelligent Automotive Lab also. He works for vehicles. So let's say every year he designs new vehicle like the ethanol based or electric vehicle or the hydrogen fuel cell vehicle, and then he goes to DOE called Department of Energy, and then he won the competition, and he received a couple of awards also for total vehicle design. On the right hand side, you can see is Professor Michael Fowler, and he is from Chemical Engineering Department, and he is my co-supervisor. So these 2 professors work together. So Professor Fraser works for vehicle and Professor Fowler works for battery and the fuel cell. So his expertise is also on the hydrogen fuel cell, but honestly speaking, I never worked on hydrogen fuel cell. So these 2, I started my research in 2010 when I joined Waterloo, and since 10 years I'm there with these 2 professors. So I have a couple of papers in reputed publications like in Elsevier, like Applied Energy, Applied Thermal Engineering, Numerical Heat Transfer, International Journal of Heat and Mass Transfer. And every year I go to SAE called Society of Automotive Engineering at Detroit, at like where we have like the auto show, and I publish so many papers every year, and these are a couple of papers from SAE. I'm also a reviewer for a couple of journals, and I reviewed more than 800 articles, including desalination, energy, applied thermal engineering, energy research, and all those stuff. In 2018 and 19, I was identified as a top reviewer, which you can see over here. And this slide now, couple of 3 to 4 slides after this are very important for those who would like to come to Canada, especially at University of Waterloo. Now, let me just give you introduction about Waterloo. Waterloo is #1 university in Canada when it comes to engineering branch. When the university started in 1957, there were only 74 students. And right now you can see there are like 41,000 intakes. So that was the highest intake in Canada. And it is one of the, that is why it is identified as #1 university in Canada. In continuation of that, I would like to play a small video about Waterloo so that you can have an idea. And just for your kind information, Waterloo is growing because the Google headquarters is moving from Silicon Valley to University of Waterloo. So let us see. She won the Nobel Prize just now. And he is Vice Chancellor of University of Waterloo. So this is something about Waterloo, and in one of the slides you saw a lady professor with the in front of whiteboard, and her name is Professor Donna Strickland, and she recently won the Nobel Prize, and she is the first Canadian lady who won the Nobel Prize. And in the last slide, I explained that Professor like Faridun Hamdullahpur, he is also from mechanical department, and he is a vice chancellor right now. So in continuation of this slide, okay, this slide is very important for the student, those who are in MTech or undergrad, and they would like to come for PhD or masters. So to enter at the University of Waterloo, your first requirement is very good score in IELTS. Now, there are 2 types of master degree in Canada. One is called MASc, called the Master of Science or MS, where you have to do 5 graduate level courses in 1 year, and you have to do the research in the next year, and you can write 2 or 3 journal papers, and you can go out from the university with master degree. But keep in mind that Master of Science is the funded program. So the professor will give you money for at least 2 years. So that is called MASc. Second one is called the M.Eng, called Master of Engineering. It is not a funded program. Basically, you will not get any money from any professor. But in M.Eng, you have to do only 9 graduate level courses, and you don't have to do any research. You don't have to write any paper. But keep in mind that if you come to Waterloo for M.Eng, you have to pay money from your own pocket. So you will not get anything from University of Waterloo or anything from the professor. Usual cost is $15,000 per year, and the program length is around 2 years. The third one is important one is the long program called the PhD, and PhD is usually funded program. So when, let's say, if I want to hire any student, there is a bond between student and a faculty, he or she cannot leave the student, or student cannot leave that professor. So it's a long time commitment. And in PhD, you have to do 4 grad level courses plus research and plus 5 journal papers. 5, you can write 4 also, but with the 5 journal papers, now University of Waterloo has started the new thesis called the paper-based thesis. So you can just copy and paste your 5 papers and that's it. Recently, they started the combined program called MS plus PhD, in which you have to do, instead of 5 like papers or 5 grade level courses, you can do 7 grade level courses and plus research, and you can finish your master's plus PhD in 5 years also. Now, keep in mind that all universities in Canada are according to CEAB, called Canadian Engineering Accreditation Board. So you don't have to worry about the fake degree or fake university if you want to come to the Canada. Now, we all know that the Waterloo is good university, but having said this, there are other good universities also. UBC is called University of British Columbia, which is in Vancouver, and that is also topmost university, and biggest plus point for Vancouver is there is no snow at all. Then after U of T, known as University of Toronto, is also very good, and McGill University, that is in Quebec province in Montreal, that is also one of the topmost university for the medical branch. Some other good universities are U of Alberta, U of Saskatchewan, Manitoba, then Capital University called the University of Ottawa, and McMaster University, which is located on the QW highway between Toronto and Niagara Falls. And good universities for M.Eng are Carleton, Windsor, Western Ontario, Ryerson, Gulf, and Concordia also. So this is just a small idea about M.Eng and PhD at University of Waterloo. Now, let me jump to my technical topic about the battery. What is battery? We all know that the battery is actually number of electrical cells connected either in like series or in a parallel. And the cell is a combination of 2 electrodes arranged so that oxidation reaction takes place, which produces electromotive force. Now, there are 3 types of battery: primary, secondary, and the reserve. So primary battery is one which is not a rechargeable. So once you are done, you have to throw that battery into garbage. The best example is the Duracell or the alkaline battery, zinc carbon, zinc air, or the lithium metal. The another type of the battery is known as the secondary cell or battery, which is the rechargeable battery. Means you can charge and discharge number of times. And the best example is our 12-volt battery, where you can start your car. Then after the lithium-ion, nickel cadmium, nickel metal hydride battery. Now, cell, module, and pack. So cell is the smallest element in the pack, which you can see over here. And the voltage range is between 0 to 6 volt. Module is something like this one, where number of these kind of single cells are connected either in a series or in a parallel. And pack, you can see over here, number of modules, let's say 1, 2, 3, 4 are connected in a series or in parallel, depending on your voltage and current requirement. And this is the Tesla battery pack, which uses the cylindrical battery it's like the Tesla Model 3 and Model X also. Common units we all know is the voltage, current, capacity is the amp power, that is the equivalent to the coulomb. Now the new terminology is the SOC, known as the state of charge, is the measure of charge remaining in a battery relative to its full or empty state. And DOD, known as the depth of discharge, is opposite to the SOC. So let's say your battery is 60% SOC, then you can say the DOD is 40%. The another example is, let's say SOC is how much petrol is there in the tank, and depth of discharge is how much petrol is removed from the tank. In continuation to that C rate and E rate, so the charge and discharge current is measured in the C rate. So if you look at the 1C, so 1C is basically, and your capacity is 100 amp hour. So you can say the 100 ampere constant current discharge in 1 hour is known as the 1C rate. Opposite to C rate, it is known as the E rate. Power, we know that the V into I, whatever is the energy, whatever per liter is energy density, whatever per kg is specific energy, then specific power and the power density. State of health is the new term, is the measure of battery condition compared to its initial or ideal state. and it is the measure between beginning of life and end of life as a percentage. Those who are in electrical, they must know about the OCV, known as the open circuit voltage, which is the voltage when there is no current passing through the circuit, and subsequently there is no chemical reaction occurring within the battery. Now, terminal voltage is the voltage which is measured between the battery, means the positive and negative electron, when the load is connected. Nominal voltage is the reported voltage or the reference voltage or manufacturer supplier voltage, and the cutoff voltage is the minimum voltage which defines the empty state of the battery. Charge voltage is the voltage at which the battery is fully charged, and float voltage is the voltage like when the battery is maintained after reaching 200% state of charge. So this is the end of the terminology part, and now the lithium-ion battery. If you look at this table, it gives the comparison of lithium-ion with nickel metal hydride and lead acid battery, and you can see the green color like points where nominal cell voltage for lithium-ion battery is very high, up to 3.7. Specific energy is up to 220. Specific power is 600 to 3400, and cycle life is very good, up to 8,000 times. So you can charge and discharge lithium-ion battery up to 8,000 times, and that is why lithium-ion battery is the most advanced battery technology nowadays used for small devices like wristwatch, laser pointer, laptop, slide changer to the hybrid and electric vehicle. So here, then after types of batteries, as we all know that the coin batteries are used for wristwatches and small devices. Cylindrical batteries are used in the electric vehicle, and prismatic as well as the pouch batteries are also used in electric vehicle nowadays. Cell operation, since this is the fundamental part, I would like to skip those couple of chemical reactions. But so main components for lithium-ion battery are anode, cathode, and there is a white color separator sheet between anode and cathode. Now, during discharge mechanism, the current flow from cathode to anode, electron travel from anode to cathode, and there is a separator sheet between anode and cathode. So lithium-ion travel via separator sheet towards the cathode. So this is the positive, negative, and overall reaction, and I would like to skip these equations at this point. Then again, chemical reactions part is not that much important, but those who are in mechanical and in electrical and who like to work on electrochemical thermal model, it has like 79 parameters and so many governing equations, but I will not go into that deep right now. So, but just the parts are like the positive current collector, negative current collector, and there is a separator sheet, the negative electrode and positive electrode. And here you can see the A4 size battery, or you can say the prismatic battery. Then after, the cathode chemistry defines the lithium-ion battery, which has three cathode chemistry. One is the lithium cobalt battery, which you can see over here, layer structure. Second one is the cubical structure, which is known as the lithium manganese. And the third one is the olivine structure known as the lithium phosphate battery. So this is the cathode chemistry, and anodes are usually graphite and silicon. Just to give you a small idea, there is a company in California called, I think, Innovate, and the CEO of that company is Dr. David Park, and he has, I think, 11 to 13 patent, and he is claiming that he has developed the new battery with the silicon-based anode, and he is claiming that your battery charging is going to be very fast. Instead of like 1 hour, it is going to be like only 15 to 20 minutes. The separated materials are ethyl carbonate, diethyl carbonate, ethyl methyl, and the dimethyl carbonate. So after this, I would like to play a small video about the manufacturing process for the lithium-ion battery, which has like the anode, cathode, and separator, and how they manufacture the battery with the LG Chem stuff. So just for your kind information, the 5 dominant electric vehicle battery manufacturing companies are: one is the LG, second one is the Samsung, third one is the Continental, fourth one is very good Chinese company known as CATL, Contemporary Amprex Technology Limited, and then the Bosch. So the Bosch has recently like launched so many batteries, and even Tesla batteries are also available in the market now. So now let me go with my research part. So if you look at this slide, that is from the Esso company in Canada. So the gas price was 52 cents per liter, and it is increased to $2.93, so which is very high. And even if you look at this slide, that is according to Environment Canada, the highest contribution to the greenhouse gas emission is from transportation sector, that is around 32%. Due to all this, the CO2 concentration profile is continuously increasing since 1960. And here you can see the latest figure in 2020 is around 410 parts per million. Due to all these factors like gas price, pollution, and CO2 concentration profile, we have to find out the alternative for this gasoline car, which is known as the electric car. And main heart of this vehicle is the battery or battery pack. And the problem with this battery is explained in this problem definition slide. If you look at this slide, this is the General Motor Chevrolet Volt car, which has around 288 batteries like this one into 9 module. So something like this one with 55 to 60 mile with a fully charged battery pack. And this is the surface temperature distribution for this single battery cell by pasting one thermocouple somewhere over here at 1C, 2C, 3C, and the 4C discharge. Now, as I explained, the C rate is the charge and discharge current of the battery with respect to its nominal capacity. So in General Motor, they used a 123 battery with 20 amp hour capacity. So 1C means 20 ampere, 2C means 40 ampere, 3C means 60 ampere, and 4C means 80 ampere constant current discharge. If you look at higher current rate of the 4C means 80 ampere, we can say that enough heat is generated in this battery to increase the cell temperature from 22-degree cold start condition to up to 60 degrees centigrade. Now, this value is for a single battery cell where there is no free, where there was a free air convection during experiments. But when it is extrapolated to approximately 300 batteries into this battery pack, there is no free air convection, but only conduction occurs between each cell, which results into enormous heat generation. And therefore, during high power discharge, so let's say if you drive the car with more than 125 kilometers per hour, battery high operating temperature above 50 degrees centigrade affects 3 basic parameters. First one, battery performance, which ultimately reduces electric vehicle range. So you will not, instead of 150 kilometer range, you will get only 100 kilometer. Second thing, aging or degradation, and sometimes there is a fire or explosion problem is also there. So, which you can see somewhere over here. So to achieve the optimum performance from a battery pack, a robust battery thermal management system is required to operate the batteries in the desired temperature range, which is between 10 to let's say 35 degrees centigrade, and to reduce uneven temperature, voltage, and associated distribution, and for good and long battery life also. Before going into my research part, I would like to give a small idea about the hybrid, plug-in hybrid, and electric vehicle. This is from Chrysler Pacifica, and this is the only one car in SUV which is available with the hybrid version. So hybrid car is one in which it has like the battery pack plus like electric motor. Second one is somewhere over here, you can see that is from Fiat company, so Fiat 500. But PHEV is a type of hybrid, but it has a different range. So let's say PHEV 40 and PHEV 60 mile means 100 kilometer. Let's say if you want to drive a car within Baroda city, you can go up to PHEV 60 or 80. And so depending on your requirement, you can buy the PHEV. And full electric vehicle is one in which there is no engine. It works only with the battery and the electric motor. This is the Jeep Compass, and for your kind information, in Jeep Compass is launching electric version in 2023. So this is something about hybrid, plug-in hybrid, and electric vehicle. Then Transport Canada project. I don't want to go into these, all these paragraphs, but just to give you a small idea about the project. The title was Battery Life Cycle Management for plug-in hybrid and electric vehicle. And there were 4 tasks. One is the data management, second one was modeling, third one model validation, and fourth one the secondary use of battery. To give you an idea about that project or that vehicle, it was the first Canadian electric vehicle, which you can see over here on the right hand side. So zero emission, pure electric vehicle. So the company called REV, called Rapid Electric Vehicle, that is in Vancouver, took out the engine from this Ford car and then put the engine and put the battery pack and the electric motor. So it's a pure EV, and other 2 are the hybrid electric vehicle, where you can see the engine plus battery pack. So I took 3 vehicles, and then after you can see this data logger. So this data logger was installed in this electric vehicle, and then we received the data. But before going into that data logger, I would like to give a small idea about this pure electric vehicle, where you can see it has like the UQM motor that is 125 kilowatt capacity. Then we change the charging port also, like the new charging port that is with the level 2. So chargers are available with the level 1, 2, and 3. And usually we use the level 2 charger, which takes around 4 hours to charge the vehicle. Now the vehicle mass, motor peak power, motor torque, and battery module energy density was 89 kilowatt per kg, and total battery pack. So this vehicle has 25 kilowatt hour energy. Then after, you can see here the pack, module, and cell. So this electric vehicle has 3 battery pack. First battery pack is located at front of the vehicle. Second battery pack and third battery pack are located at middle and end of the vehicle, which you can see in the CAD view also, and which you can see somewhere over here also. The first battery pack has around 6 modules, which you can see over here, and they are connected in a series. And each module has these kind of cylindrical cells, which you can see over here. Now, which is 18650. So 18650 means 18 millimeter diameter and 65 millimeter is the height of the cell. Now, let me go to mathematics. So each module contains 6 series multiplied by 49 parallel, which gives around 294 multiplied by 20 modules. So all together, 3 battery pack has 20 module, which gives like around 5,800 cylindrical cells. And each cell, like so, battery pack has 3 number of module 20. Nominal operating voltage is 3.2, and capacity of this cell is only 1.4 because it is a cylindrical cell. So this is about the electric vehicle. And then after, this kind of Isaac data logger was installed in this electric vehicle, which you can see over here below the passenger seat. And then after, the laptop was connected to collect the data during the driving. Here somewhere you can see the 12-volt shutdown wire, and then after the GPS, called the global positioning system, for the data collection during the driving and during the charging also. Couple of important signals for electric vehicle modeling are battery voltage, current, all 20 module temperature, state of charge, motor torque, motor speed, brake pedal position, and the vehicle speed also. After installing data logger, what I did is I draw the vehicle, so this electric vehicle, from Toronto, means Greater Toronto, to the Niagara Falls, and then Niagara Falls to Toronto back on the highway called QEW, called Queen Elizabeth Way. This is one of the busiest highway in Canada because it connects the Buffalo, means like the US border. So when I started the trip, I found that all 3 battery packs were fully charged with the state of charge 100%, and the vehicle. So, and when I ended my trip to Niagara Falls, the total trip distance was 106 kilometers. So Toronto to Niagara Falls is 106 kilometers, and at the end of my trip, the SOC was 2%, and total energy consumption, as I said, that all 3 battery pack has 25 kilowatt hour. So total energy consumption was 23 kilowatt hour. Now, trip cost at 11 cents per kilowatt hour. So in Canada, in Ontario province, in Toronto, the electricity cost is 11 cents per kilowatt hour. So to trip cost means this 106 kilometer, to drive the 106 kilometer, the cost is only $2.60. So it takes only $3 to reach to Niagara Falls. And if you go with your gasoline car, it takes almost $25 gas. So that way I wanted to conclude that the electric vehicle is much more affordable in operation as compared to the other gasoline vehicles. Just for your kind information, when I drove the vehicle in November month, the outside temperature in Canada was plus 5 degrees centigrade. Then after this kind of energy and cost analysis was done for this particular vehicle in terms of total kilometer driven, then time, then driving energy, charging energy, energy path, temperature, and then this kind of reports on monthly basis were generated, and it is available in the Transport Canada website also. Just to give you idea about that longest drive cycle from Toronto to Niagara Falls, which you can see over here, the vehicle speed in kilometer per hour versus time, where you can see over here, the vehicle was driven with maximum speed of 125 kilometer between this one, 1000 to 3000 seconds. And then after, you can see here so many ups and downs. Those ups and downs are because of the heavy traffic on the highway. So the speed was almost zero, and then after, so this is the highway driving. Then after, you can say the stop and go. Corresponding voltage and the battery current profile are presented over here. All 20 module temperature profiles are presented in this plot, and green color line, which you can see, is the battery state of charge. So starting SOC was 100% and ending SOC was 0%. So this is about the drive cycle details. And after that, the vehicle was driven on the same path between October to February, and it was found that the vehicle was driven for almost 800 kilometers for 5 months, and driving cost is only $20 to drive the 800 kilometers. Then comparison was done with the other two hybrid electric vehicle with this electric vehicle, and it was found that this vehicle is much more affordable in operation as compared to other two fleet vehicle called the hybrid electric vehicle, with the same mass and the same like dimensions and everything. This is the end of second part. So the first part is the data logger installation. Second part is the data management. Third part is the very critical and important part is called the model development. So a model for electric car was developed using the PSET called Powertrain System Analysis Toolkit software, and the latest version is known as the Autonomie software. And this electric vehicle was designed, and you can see the architecture for this vehicle where important components are the battery, then after the motor, then torque coupling, differential, wheel, then vehicle, DC-DC converter, and electrical accessories. And just for your kind information, when I design the vehicle or when you model any vehicle, let's say in Baroda, where we have flyover, maximum angle we take around 7 to 8 degrees. But when I design the vehicle for North American region, including Canada and America, we go up to 10 to 11 degree. That is called the gradability. After that, so the first model was the electric model, but the second model was the very complicated model known as the PHEV model, because it has like the starter, engine, clutch, gearbox, final drive, wheel, chassis, means the gradability, then battery, motor, DC-DC converter, and some electrical accessories also. So when you design or when you model any vehicle, you have to consider all these major components. Then after, I don't want to go into that much detail, but this is a SimScape diagram or MATLAB simulating where you can see here the driver. So the input is the drive cycle or the driver habit, and based on that, the powertrain or driveline or the controller will give a signal to the motor, and based on the motor power, like the battery will deliver the required power to the motor. So all these three components like the motor, DC-DC converter, and the battery pack are connected on the same driveline. I don't want to go into that much detail, but just to give you a small idea, to develop the model, you need almost 300 to 350 parameters. Some of the important parameters are the energy storage system or the battery with the number of cells, number of packs, cell nominal voltage, minimum voltage, maximum voltage, mass of each battery, then number of cells in a series, number of cells in a parallel connection, and all other important parameters for the battery. The biggest component, those who are in electrical, they know about the motor. So the motor parameter, the biggest part is the torque speed characteristic curve. So based on our requirement, we have to modify, and in my model, it was UQM power phase motor 125 kilowatt. Then after, you need the motor inertia, motor maximum speed, torque, power, and controller mass and everything. In continuation of that, for PHEV, we need the engine model, and for that we need the engine mass, fuel tank mass, and everything. Gearbox, you need the number of gears, like the number of teeth on sun gear, ring gear, and all other parameters. Again, torque converter, DC-DC converter, wheel, so number of wheels. So again, when you design, I designed this vehicle for the 4-wheel drive. So you can design or you can model for front wheel drive or rear wheel drive or all-wheel drive or AWD also. Then after the vehicle mass, I consider like the vehicle mass plus 5 passengers. So driver plus 4 passenger. And then after, you have to consider the gradability, then the curb height, cargo mass, and everything for this vehicle. Brake and final drive. And then finally the controller. So you can see how many parameters are required if you would like to develop the PHEV or the EV model. So this was the third part known as the model development. And the important part was the model validation. You can see here. So this electric vehicle, as I said, was driven from Toronto to Niagara Falls and then back with a maximum speed of 125 kilometers, which you can see over here. And corresponding state of charge validation is presented over here with the model and experiment. So if you look carefully, between 1000 to 3000, so between 1000 to 3000, that is drastic reduction in state of charge. And that reduction is because of the highway driving with a maximum speed of almost 120 kilometers per hour. But after that, you can see so many ups and downs. So if you look this blue color line, that is the model, it is the straight one. But if you look the red color, that is the experimental, means the actual data received from this electric vehicle. It has so many ups and downs. And these ups and downs are related to the regenerative braking system. So I would like to highlight here that when I developed my initial model, I did not consider the regenerative braking system. Later on, I refined my model, and my model captured those regenerative braking system also. So that is the one of the important part if you develop any model. After that, you can do the validation in terms of motor input power, motor output power, and you can calculate the total energy consumption. And finally, you can find over, let's say, over 10 years, how much is the degradation or how much is the capacity fair for this battery. Another validation was done for another drive cycle called this City of Waterloo drive cycle. So only Waterloo city and the highway driving with corresponding state of charge validation, then electric motor input power validation, output power validation, and then longitudinal acceleration validation also. And then efficiency was calculated for this particular vehicle. Then after, what I did is I took the drive cycle for this vehicle. I took 4 cylindrical batteries connected in a series. I scaled down this drive cycle, fed those drive cycles into this experimental setup, which you can see over here, and I measured the thermal performance of the battery. So instead of doing those expensive experiments, so let's say installing data logger, driving the vehicle, we can take the drive cycle, we can fed the drive cycle into the experimental setup, and we can measure the performance within the laboratory also, which you can see over here, the input data and output data from the test bench. So this is the model validation part. And finally, about the degradation model. So a battery degradation model was developed based on the Thevenin approach, where you can see the open circuit voltage. So battery voltage is calculated by OCV, called the open circuit voltage, minus voltage across the ohmic resistor, minus voltage across the RC element known as the resistance capacitance element, and where V1 is calculated by IR, that is the Ohm's law, and V2 is calculated by using this equation. And the parameter for this model known as the R1, R2, and C parameter were calculated by using the HPPC, and I use the Schimlastic et al. Paper for my degradation behavior, but parallelly I measure the battery parameter using HPPC test known as the hybrid pulse power characterization test. But I don't want to go into that much detail right now, but you can see over like the model validation part, 1C charge, 1C discharge, then 1C charge and discharge for, or C/2 charge and discharge for model versus experimental part. And my another paper recently published is on the OCV, known as the open circuit voltage versus state of charge at different state of health of the battery. So let's say if you take the brand new battery, if you take 1-year-old battery, if you take 2-year-old, 3-year-old, 4-year and 5-year-old. So I took 6 batteries and I compared the OCV with the fresh battery, and then I developed the model, which you can find, I think last week it was published in Journal of Energy Storage System. So after that, the validation part is the last part of my presentation, which you can see over here. So green color one you can see on the top 3 is the dry cycle one, where you can see the highway driving plus couple of city driving and voltage validation, state of charge validation, and I did the temperature validation also. So dry cycle 2 is the blue color one. Usually you can see up to 0 speed, so it's a city driving. So only University of Waterloo or Waterloo city driving and corresponding voltage and state of charge validation. The pink color one is the dry cycle number 3 with the highway driving and the city driving and corresponding voltage and state of charge validation. And the last one is the orange one, where dry cycle number 4 is we draw the vehicle from University of Waterloo to University of Gulf, and then University of Gulf to University of Waterloo back. And then after corresponding voltage and state of charge validation. Now, statistical parameters for these drive cycles are presented over here. Drive cycle 1, 2, 3, and 4. So the drive cycle 3 is the pink color one, which you can see is recorded when outside temperature was -6 degrees centigrade. So I purposefully collected a couple of drive cycles with different outside temperatures so that we can model perfect with couple of important parameters. Then after what I did is we draw the vehicle between here July to September. So July, August, September, excluding weekend, means no Saturday, Sunday driving, only Monday to Friday driving on the same path, particularly dry cycle number 4 from University of Waterloo to University of Gulf, and then Gulf to Waterloo, including city driving and highway driving with 100 km/h is the max speed. And over 3 months of driving, I found that the capacity fed for this battery is around 4.something%, which is quite very high. But this is what it was from the experimental data. And we found that it is high because out of, let's say, the 4,000 cylindrical cells, couple of cells in the middle battery pack. So let's say module numbers 14 and 15 were the problematic one, and they were not giving the output. And that is why we need the perfect BMS known as the battery management system, and people are working in that direction right now. So I think that's it from my side, and you will find my interesting papers which I published during my research work. So during my master's, PhD and postdoc, I published almost 30 journal papers, and so you can see on Google Scholar also. And thank you so much for attending my presentation. And since we have 10 minutes, I would like to go for question answer, and feel free to ask me any question about technical topic or coming to Canada, what to do if you come to Waterloo, and if you are like, you can send me an email also. And my first name is satyam.panchal@uwaterloo.ca, and I will be happy to give question answer. So thank you so much. And now over to Unnati madam.
Thank you very much, sir. It was really a very great exposure and very insightful session from your side as far as the automotive batteries and electric vehicle is concerned. Now, I'm requesting Professor Manish Pandya, sir, to deal with the questions. He must have received few, and of course, some of the questions we are receiving in our chat box also. Sir, please.
Yeah, thank you very much, sir. Thank you very much for very nice, informative topics. Actually, we have many questions in our mind during the routine life. What is about the electrical vehicle and what about the batteries? So I think today, we have clear many things about the battery and the electrical vehicle. So thank you very much, sir, for a very excellent information about the batteries and the hybrid and the electrical vehicle. Now we have some of the questions related to the today's presentations. So one by one, I'm asking you about the questions.
Sure.
There is one question from the Professor Rital Gajar. The question is, how to get the state of the charge and state of the health for the battery?
Okay, good. So, Professor Rital, this is a good question. So, if you want to measure the SOC inside the lab, then it is very simple. Integration of current with respect to time. So, integration IT divided by dt will give you the capacity amp hour, or you can say the state of charge. But if you would like to measure for this particular vehicle, so if you can see over here, it was very tough for us to get that answer. So the company who designed this vehicle known as the REV, Rapid Electric Vehicle, we asked a couple of times that how do you measure the SOC? Then because of the confidentiality reason, they did not give that answer to us. But there is a sensor which measures the cell temperature and cell state of charge also. So based on that, you can measure the SOC. Second question, SOH. So SOH is a big phenomena. It is related to the degradation part. So degradation is another big research area, like degradation due to cycling. So number of charge discharge cycle. Number second, degradation due to high temperature. Let's say if you talk about India, where we have almost 45 degrees centigrade. And if you talk about, so degradation due to low temperature, the best example is Alberta in Canada, where we have minus 45 degrees centigrade. So that is related. So degradation occurs because of the storage, because of the high temperature, because of the low temperature, and because of the number of charge discharge cycles also. I measure SOH of the battery based on 8,000 charge discharge cycle of the battery within the laboratory. So I know that answer, but for the electric vehicle, if you want to measure state of health, you have to drive the vehicle and then you have to measure the state of health, or you can measure the capacity in amp hour and you can compare with the fresh battery and you can measure the SOH in terms of degradation phenomena. So this is answer to Mr. Rital. Are you happy with my answer, or are you clear?
Yeah, I think it is very clear.
Good.
About this one. There is
Second
one
thing
another.
is, yeah.
There is one another question from the participant. He or she wants to know about the reserve battery.
Oh,
what is
I think that is there in my one of the slide. It is not that much important, but because the important part is the secondary battery, because the primary batteries are like you can throw into garbage, but secondary batteries are important. And let me go through that part, which is the, so here, battery which is inserted until then operation is performed, which brings all the cell component into the proper state and the location becomes the active. So example is the like the missile battery, or very like the large part of the battery. Then
okay, so then the next question is, I think there is a question from the Professor DVS. The question is about if the current rate for the charging the battery of the vehicle is more than the rated value, then how can we control the current, or how the affected on the battery?
Okay, so this is something related to the charging. Now, Mr. DVS Kumar, people are working on DCFC called the DC fast charging. And just for your kind information, I cannot, disclose those R&D information, but because I'm working in R&D center also, so I'm not allowed to share any confidential information, but general idea is, so if you double the current, so right now, if you look at all these vehicles, so which on this, those are designed with the 400 volt system. So if you take an example of Tesla Model 3, which is with 370 volts, so max volt is up to 400. But now it is, let's say, electric train or electric, the construction equipment with the electric or truck, those are designed with the 800 volt. And now we are jumping into 800 volt, where the current is almost like voltage is double, but the current is half. And people are working in the control side in that area for the charging of the battery.
Okay, so basically if the current is increased, in that case there will be a factor on the battery life also. Yes, sir?
Yeah. And that is even for the charging port with the 800 volt system or with the 400, we need the cooling system also from wall to the electric vehicle charger, or let's say from charger to the vehicle.
Okay, so part of the research work, suppose, for example, say we are considering the battery rating, whatever the XYZ rating, suppose we are charging that battery with the double rate of the current. So is there any optimized technique that in this situation we are saving the energy somewhere in other part, and during the requirement we can charge and discharge that particular different part?
Yes, Dr. Manish, I'm working in that area, but I cannot share those informations. Sorry.
Oh,
Okay,
okay,
I'm
okay.
extremely sorry. Otherwise, I will be in a big trouble.
No, it's okay. Thank you very much.
But you can always search for the good paper on optimization of the DC fast charge.
Okay, okay,
Okay.
yeah, yes, yes, yes. Okay, there is another question from the participant. Can we set the induction motor on the front side wheels to generate the power for charging the battery, and back side wheels induction motor to run the vehicle?
Okay. I think his name is Mr. Arif.
Yeah, Mr. Arif.
Yeah. Okay, Mr. Arif, I am not much aware about the motor part because I'm a mechanical engineer and I work on battery from mechanical point of view. So let's say the thermal model, electrochemical model, degradation model, but I did not work much about the motor modeling at all. So I cannot, honestly speaking, I cannot give that answer to you. But yes, for the backside wheels, people are putting those for the energy part also. But I don't know honestly about this one because I'm not an electrical engineer.
Yes, sir.
But just to give you idea that Dr. Manish, we were discussing about the 800 volt system for the so if you want to design with the 800, we need the special motor and we need the special winding also, and we are working in the special winding right now for the motor.
Okay,
So this is just a small hint to you.
okay, thank you. I got the idea exactly.
Good.
Okay, another question is about the person is from Dhananjay Patil. How much battery waste is hazardous to the humans, and is this going to be the major problem in the upcoming EV era?
No, this is going to be a hot topic right now, and people are like already driving the electric vehicle right now, and it is not dangerous at all because there is no pollution for this electric car. And that is why even if you talk about California, Michigan, or everywhere in America, people are driving the electric vehicle. And nowadays, even in all shopping malls, we have the charging port over there. Even I have seen in India that in big cities like Bombay, Delhi, they have the charging port available. So it is going to be a the hot topic for the India. And for the hazardous part, that is so no, it is not hazardous because now there is another research area is the secondary use of battery. So what people are doing now, it is a big business. So they take the battery and they extract the lithium and they reuse the lithium. So that is called the secondary use of battery. So my professor is working in secondary use of battery right now.
Okay. Now another question from the Dr. Snehal Trivedi. Nowadays, the lithium-ion batteries have the shorter charging times. Is it because of the technology in the battery or the high ampere charges?
No, it is because of the material. So, like as I said, that in California there is one company called Enevate. You can type the name ENEVATE, and his CEO designed a new battery called the silicon-based anode. And due to change of material, the charging is very fast. And even with the DC fast charging, like you can charge the vehicle quickly. So, Dr. Snehal Trivedi, okay.
Yes.
Then after
another
we have
questions.
Aditya Soni.
Yes.
Okay. Is the mobile phone fast charging and vehicle fast charging similar? Yes, but see, for vehicle we have high range, so like high voltage and current. Okay, so and number of cells are connected in a series or in a parallel. And so depending on your vehicle, so let's say if you design the vehicle with, if you talk about Tesla Model 3, it is designed with 370 volt. So you can imagine like you need the minimum level 2 charger. And for mobile, it's you can see the fast charging. Yeah, it's possible. Mr. Jagdish, which standards or norms that need to follow for electric vehicle manufacturing? Oh, that is a big one. Just type Chrysler.com or TMMC, like Toyota Motor Manufacturing Company.ca, and you will find those standards or those requirements to follow the electric vehicle manufacturing. Mr. then after the next one is how to know the remaining life cycle of the lithium-ion battery if we have cell in hand and diesel generator with 5 kilowatt output. Okay, if we have cell in hand, then we can measure the remaining life by measuring the amp hour capacity. So let's say if you buy the new battery, then and you know the capacity like with the manufacturer's recommended. So let's say cylindrical battery 18650, so 1.4 amp hour capacity, and after 6 months, if you discharge the battery and you can measure amp hour capacity, that way you can design or you can measure the remaining life of the lithium-ion battery. How can we improve the battery life or reduce charging time? Okay, so reduce charging time, you can go for either DC fast charge, or you can improve or you can charge the car with the level 3 charger. What are your thoughts on the new Tesla battery model? Okay, he recently published a new article. I would like Mr. Malek to read Mr. Elon Musk. So he's the CEO of Tesla company. So he recently introduced the new thought about the new Tesla battery module. So just have a look for that video also. Apart from technical, any question about coming to Canada or Waterloo University, what to do or something like that one?
So, Dr. Satyam, this itself is a great success, the way series of questions we are receiving. And of course, most of them has been answered. I think still a few are maybe in a pipeline. Sure. So, I think based on the time, and now we need to end up with this session. And definitely to all the attendees and participants, of course, feel free to send the queries if you do have still. And we will convey this to Dr. Satyam, and definitely, sir, based on this, we would like to have you once again for such kind of the innovative topic. And thank you very much on behalf of Faculty of Engineering and Technology, Waterloo University. I thank you very much, sir, for as you spent your time. And it was really a very interactive session, and definitely the way questions were being raised, I think they have enlightened a lot. Thank you so much, sir.
Good. Before I end my from my side, I would like, if any faculty or any M.Tech students or PhD student are working in the electric vehicle side, and if they need the experimental data from my laboratory, so especially from University of Waterloo for vehicle as well as for the battery, then I will be happy to provide those experimental data, and that way we can do the collaborative work with Parul and with you, Waterloo, also.
Surely, sir. This we will take it forward, and in this regards, we will be contacting you, sir. Thank you very much for this great proposal. Thank you so much for today's webinar.
Okay, so thank you so much, everyone, and send me an email if you have any question after this one. Okay, so thank you.
Sure, sir. Thank you so much.
Bye.
See you again.